All right, guys, lesson 1.3. Today we're talking about infinite limits and limits at infinity, which sound almost the same, but they are very different things. And we'll get into that as we go through this. But a couple of things from the past that you need to remember. Some of this is Math 3 stuff. Some of this we've already talked about a little bit this year. But a couple of review things. Here's a function. It wants to know where the holes in the function are. So you look at what cancels on the top and the bottom. That x minus 1 would cancel, which means that there is a hole when x is equal to 1. I don't know what the y value is, and I don't want to take the time to find it, but I know that there's a hole at that point on the graph, okay? An even vertical asymptote. So vertical asymptotes, remember, again, we're looking at what is going to make the bottom 0, but doesn't cancel out. And in this case, I have x minus 2 squared and x minus 4 cubed. Both of those make vertical asymptotes. The difference is in the 2 and the 3. Okay, if the exponent is even, then that makes it's called an even vertical asymptote. So at x equals 2, we would have an even vertical asymptote. And if you look down below, all that means is that both sides of the asymptote, notice how my graph is going the same direction. So over here on the left, I'm going up. On the right, I'm going up. On the left, I'm going down. On the right, I'm going down. That is called an even asymptote. An odd vertical asymptote is when I have a odd exponent. So that would be my x equals 4. And all that means is that to the left, if I'm going down, my function, to the right, I'm going up. And vice versa. If I'm going up to the left, to the right, I'm going down. That's called an odd vertical asymptote. Okay, so what we're considering today, first we're going to talk about infinite limits. Now, you've seen examples where a limit does not exist at these vertical asymptotes. Now, these limits can be expressed as infinite limits if the vertical asymptote is even, or if you're finding one-sided limit. So what we've done in the past is you're given a limit to find, and the first thing you try to do is direct substitution. Sometimes that doesn't work. So then you try to redo the equation, cancel things out, factor, and eliminate. You try to cancel things out, factor, and move things around. Sometimes that doesn't work. And that's what we're talking about today. What if you can't direct substitute? What if nothing cancels out, but you still have things left in your function, okay? And that's what gets us to start looking at infinite limits. So a lot of times when this happens, you have an asymptote, which means that your limit, what's happening to your graph, is there's not a hole. Your graph is going up to infinity or down to negative infinity, all right? Just like it has in the past, all of these limits that we do today, if you're ever saying, if you look at this sentence right here, we're going to write the limit as x goes to c of f of x equals infinity. The other option would be to say that it does not exist. Or the limit as x goes to c of f of x equals negative 8. Does not exist would always be an option as well. Okay, so here's what it looks like. Couple examples, and it'll take that nonsense and kind of put it into something you can use. So I have this limit as in example number 1. As x approaches 2 from the right, I want to evaluate x plus 3 over x minus 2. I want to know what's happening. Well, I can't do direct substitution because I get a 0 on the bottom. Nothing cancels or eliminates. I can't do any cool math tricks to make something go away. So I'm kind of stuck. So what I'm going to do before I walk away is I know that there's a good chance that this means I have a vertical asymptote. So if I'm looking at what's happening at this point, I'm going to do what's called not that one. We're going to use what's called Sine Analysis. And you should have done this kind of in other classes, not using limits, but looking at sines. So for example, I'm considering numbers that are a little bit bigger than 2 because I'm approaching 2 from the right. So if I plug in something on the top that's a little bit bigger than 2, I'm going to get something a little bit bigger than 5, which is a positive number. On the bottom, if I plug in a number a little bit bigger than 2, the closer I get to 2, the closer I'm actually getting to 0, right? But I'm a little bit bigger than 2, and then I subtract 2, which means I'm a little bit bigger than 0. I'm not exactly 0, I'm positive. I'm a little bit bigger than 0. So I have a positive number on the top and a positive number on the bottom. What that tells me is that my limit is actually infinity. I have a vertical asymptote on this problem, and I am going to infinity. And it's that easy. Okay, number 2, what happens as x approaches 2 from the left? Same function, but now I'm approaching 2 from the left side. So I can't plug in 2 because I get a 0 on the bottom. Nothing eliminates, nothing cancels, just like it didn't before because it's the same function, duh. So let's look at numbers. Let's look at our sign analysis. If I plug a number a little bit smaller than 2 on top, then I get a number around 2 plus 3, and again, that's kind of about 5-ish, but I'm at a positive number. That's the part I care about. If I take a number a little bit smaller than 2 and put it on the bottom, something like 1.99, and then I subtract 2 from it. Again, I'm getting really close to 0, but I'm smaller than 0 because I'm subtracting a bigger number. So my bottom is a negative number. Some number, I don't know what it is, but it's negative. My top is positive. So instead of going to infinity, a positive over a negative means I'm going to negative infinity. I'm going to negative infinity. Okay, now number 3. Limit as x approaches 1 from the right. So a number a little bit bigger than 1. When I plug that in on top, I end up with a negative number because 2 is bigger than 1. When I plug that in on the bottom, so let's say the number is like 1.001, and then I minus 1, I get a little tiny number, and then I square it. But whatever happens, it's a positive number. So I have a negative on the top and a positive on the bottom. So that means I have a vertical asymptote, and I'm going to negative infinity. All right. Now looking at, before we move on to examples 4 and 5, I know yours are really close, but one other thing that I forgot to mention, if I look at my denominator right here, x minus 2, technically there's an exponent of 1 right there. And if I do the same thing right here, technically there's an exponent of 1 right there. So that means that my vertical asymptote is going to be an odd vertical asymptote, right? Because I only have an exponent of 1, of an odd number. So whatever's happening on my graph, it's going different directions at that asymptote. One side it's going up, one side it's going down, okay? Number 4, x minus 2 on top, x minus 1 squared on the bottom. And I want to plug in a number a little bit smaller than 1. I'm approaching 1 from the left, right? So nothing cancels, no trickery here. So let's just look at the signs of what's happening. When I'm a little bit smaller than 1 and I plug that number on top, I end up with a negative number because I'm subtracting 2. When I plug that number on the bottom, it doesn't really matter what's happening inside the parentheses. Whether it's a positive or a negative number, I'm going to square it, which means I'm going to end up with a positive answer. So I have a negative on top, a positive on the bottom, so that means my limit is negative infinity. And if you want to know what these look like, graph them, take a look at it. When we go over this in class, we'll actually look at these functions so you can see what's happening. I don't want to take the time to do that on the video. That's 5 minutes that you can take yourself. This one's a little bit different though, because the bottom has an x minus 1 squared. And what that squared means is that this is an even vertical asymptote. So that means that if this is my vertical asymptote, both of my functions are going down to negative infinity. On both sides of the asymptote, they're going down, okay? Whereas before, on these odd ones, when I was to the right, if my vertical asymptote's right here, to the right, I was going up, to the left, I was going down, okay? All right, number 5, x squared minus 4 over x minus 2. I can't plug 2 in directly. I get a 0 on the bottom. But this one looks like I can maybe reduce something on the top, because that's my fancy difference of squares formula. So let's rewrite this. The limit as x approaches 2 of x minus 2 on top, x plus 2 on the bottom, over x minus 2. Now those are going to cancel. And I'm left with the limit as x goes to 2 of x plus 2, which is just 4. So I don't have a vertical asymptote at all. I'm actually going to approach, my limit is 4, but I know that there's a hole. There's a hole at 2 comma 4. At that point, there's going to be a hole. I don't know where the function goes from there, but I do know that there's a hole at the point. So no vertical asymptote on that one. So those are infinite limits. Okay, those are when the answer to our limit is infinite. It's an infinity answer or does not exist. The next topic is what happens if we evaluate limits at infinity. So instead of our function going to infinity, what happens if we take the limit as x approaches infinity? What's going to happen there? So just kind of reading through what's here, you can pause and do that on your own if you want, but it says if the graph of a function approaches a horizontal asymptote, f of x is said to have a limit at infinity, which makes sense, right? If I have a function, let's make up a function here, and there's an asymptote like this. Now remember, these asymptotes go forever. It doesn't matter what's happening to my function. At the end of my function, I'm getting really close to that, but I'm not actually crossing it. So it's kind of telling me what's happening at the end of my function, right? As I go to infinity, I'm getting really close to that asymptote. So if the asymptote is y equals L, I'm just back to reading, then the limit as x goes to infinity of f of x equals L. In other words, limits at infinity tell us what the end behavior is doing of our graph. It tells us what's happening at the end. What's really cool about that is I love when we just start assuming that we're plugging in really big numbers, that we're going to infinity, because what that does to our function, like look at number 6. Number 6 has all kinds of stuff going on, and it wants us to find the horizontal asymptotes. Well, the way that you would do this, number 6, 7, and 8 want us to do this the way that is kind of a review of secondary math 3. So what you were taught in secondary math 3 to find horizontal asymptotes, you would look at the biggest degree on the top, which is right here, x to the 4th, and the biggest degree on the bottom, which is also x to the 4th. If those degrees were the same, okay, if I had, and this might be something you want to add to your notes, if those were the same degree, you were taught to look at the coefficient in front. So if I'm looking at 5x to the 4th, 10x to the 4th, all I really care about is the 5 and the 10. And here's why. As these numbers get really, really, really big, x to the 4th is going to become so much bigger than x squared and 2 and 3, that none of those numbers even are going to matter. If I'm going to infinity, if I'm making x ridiculously huge, all those other numbers mean absolutely nothing. All that I'm interested in is whatever's in front of the x to the fourth, and that's a 5 on top and a 10 on the bottom, and if I simplify that, I get 1/2. So in math 3, you would have said, oh, there's a horizontal asymptote, and it's y equals 1/2. So then going to number 7, I'm going to look at the same thing. I'm going to look at the biggest degree on top, which is 5x to the fourth, the biggest on the bottom, that's 10x to the fifth, and this is what we call bottom heavy, because the degree on the bottom is bigger than the degree on the top, right? So what happens is, again, none of this even matters, because I'm going to start plugging in infinity, and that's going to make x to the fourth and x to the fifth exceptionally huge. The difference is the bottom is going to get bigger a lot faster, right? Because on the top, I only have 5x to the fourth. On the bottom, and the 5 doesn't even matter. I have x to the fourth on the top, and I have x to the fifth on the bottom, which means the bottom, because of that x to the fifth, is going to get bigger way faster than the top. And what that tells me is that what you would do in math 3, you would say, okay, since the bottom is going to get bigger faster, then I'm going to have a horizontal asymptote at y equals 0, because the bottom is so much bigger than the top. Now, there's also situations like number 8 that you learned about. What about when the top is bigger? Now, in secondary math 3, if the top has a bigger degree than the bottom, you were taught that there is no horizontal asymptote, which is absolutely true. There is not a horizontal asymptote. There is, and I can't remember what they call it, like a slanted asymptote or something like that. You have an asymptote that goes like this. It's not vertical, it's not horizontal, it's on some slope. It has some angle to it, okay? So there's your review of how you did this in secondary math 3. What I want to consider is calculus. Instead of looking at the function, I want to evaluate the limit as x goes to infinity. And pretty much, I'm going to use the exact same rules. The only thing that matters is the biggest degree on the top and the biggest degree on the bottom. If they are the same, then I look at the coefficients. So these ones are the same. In fact, these are the same problems, right? As above. The x to the fourth on top and the x to the fourth on the bottom. So all I care about is the 5 over 10, which is going to simplify to 1/2, which tells me that that is my limit. My limit is going to be 1/2 as I go to infinity, which makes sense because that's where my asymptote is. Right? Now number 10 looks like the one right above it. I look at my degrees and my degrees. This one is bottom heavy. It's the words we're going to use. It's bottom heavy because x to the fifth is bigger, and that means the exact same thing it meant in math 3. The bottom is so much bigger that as I go to infinity or negative infinity, it doesn't matter, my function is going to go to 0 because I'm plugging in infinity. Same answer. Here's where it gets different. In calculus, when I run into the situation number 11, I'm taking the limit as I go to infinity. On top, I have an x to the fourth. On the bottom, I have an x cubed. So that means that this is top heavy. And you were taught that that means there's not a horizontal asymptote, which is true because there's a slanted asymptote. So what does that mean about my function? That means that my function is doing something, but eventually it starts going like this. So what is my function approaching? as I go further and further and further to the right, my function is approaching infinity. My top is getting so much bigger than the bottom, I'm approaching infinity. Or, just like in the past, we could say that it does not exist. Okay, let's look at a couple more. Number 12, as x approaches infinity, and there's all kinds of stuff going on. 2x plus 3 on the top, x minus 1 squared on the top, x plus 2 on the bottom, 3x minus 1 squared on the bottom. All of these things are happening. But I'm looking at what happens when x goes to infinity. So I know that what I care about, remember in this previous problems, we cared about the biggest degree. And I put a note over here that you don't consider, it says make sure you consider the highest degree term, not the highest degree factors. What that means is the highest degree is not 2 and 2. It's the highest degree of an x term. So if I were to take this whole top and multiply it out, if I were to take everything on top and multiply and FOIL and do all that big ugly mess, and then I'd have to times it by another x minus 1, basically what I'm doing is multiplying everything together. And when I do that, I'm going to rewrite this. If I were to multiply everything out on the top, the only thing I care about is my x value, okay? I'm going to take my 2x, and it's going to get multiplied by this x, and that's going to give me 2x squared. That is going to get multiplied by another x, because this is x minus 1 squared, so there's actually 2 of them. So I've got 2x multiplied by x, that's 2x squared, and I'm going to multiply by x again, so that gives me 2x cubed. Now on the bottom, I'm going to erase this square and I'm going to rewrite 3x minus 1 because there's 2 of them. X is going to get multiplied by 3x, so that's 3x squared. And that's going to get multiplied by another 3x, and that's going to give me 9x cubed. Obviously, that is not everything. There's going to be a whole bunch of other terms on top. But because I'm looking at when x goes to infinity, I don't care about anything else. The only thing I care about are these 2 biggest degrees. And they're the same. Okay, so I have the same on top and on bottom, which means I'm supposed to look at the coefficients. So I've got a 2 on top, a 9 on the bottom. That means my limit is 2 over 9. So that big ugly thing, the limit as x goes to infinity, is just 2 over 9. That's all you have to do, is consider the biggest x degree. Okay, couple more. I keep saying that, huh? Do you feel like I said a couple more 18 ago? Well, that's not true because I'm only on 13, so you're exaggerating. Rational functions like the ones that we did up above, they have at most one horizontal asymptote. So it doesn't matter if I'm going to negative infinity or infinity. Either way, I'm approaching the same asymptote. Radical functions, though, sometimes they can have 2 asymptotes. So I wanted to show you what this looks like. This is another cool use of plugging in infinity, because if I look at this, number 13, x is approaching infinity. So as I plug that in on the top, this minus 3 is going to become so inconsequential, I don't even care, which just leaves me with 4x squared. Well, sorry, the square root of 4x squared. So actually, I can, instead of considering that it gave me, the square root of 4x squared, that's just 2x on top and x on the bottom. Now, I'm not, guys, understand, I'm not changing my function, but I'm evaluating it at infinity, so I'm writing it a little bit different because I don't need to consider all the pieces. Because again, that minus 3 is going to mean absolutely nothing when I'm plugging in infinity. The only thing that matters is my exponents. So if I have a 2x on the top and a 2x on the bottom, well, technically this should be the absolute value of 2x because it could be a positive or a negative version, right? As I go to infinity, the top is going to end up being a giant positive number. The bottom is going to end up being a giant positive number. But my degrees are the same, so all I'm really interested in is the 2. So my limit is 2, and it's a positive 2, which is why I check the positives. Number 14 wants me to take the limit as x goes to negative infinity. If I'm plugging in negative numbers, this doesn't mean anything at all. So I can rewrite this. The limit as x goes to negative infinity. And for the square root of 4x squared, well, that's pretty much 2x over x. And I won't forget my absolute value this time. But here's what's going to happen. I'm going to plug in a giant negative number. On top, that doesn't matter because I still end up with a positive on top. But on the bottom, I end up with a negative because it's a giant negative number, right? So I'm still going to the number 2. My limit is still 2, but this time it's a negative 2 because my number on top is positive and the bottom is a negative. So my answer is going to be negative 2 instead of 2. So this function, if you were to graph it, you would see 2 horizontal asymptotes. You would see, if this is my function, you're going to see one at 2 right here, and then you're going to see one at negative 2 down there. There's going to be 2 different horizontal asymptotes. All right, 15, 16, 17, 18, and I promise these are the last 4. It wants us to use the end behavior of y equals e to the x to find these limits. So what happens if I'm given a limit with e to the x? Well, if you know anything about e to the x, which, you know, you're all in calculus, you've gone to school for a few years, so hopefully you at least know that it looks like this. If you forgot and you have to graph it to remind yourself that's what it looks like, that's okay. That's why we're practicing. This point right here is actually e, right? No, that's not e. That's going to be what? If I plug in a 0, that's going to be 1. E is going to be right here at 1. So this value right here is going to be e. So this is what, and numbers don't matter. This is just a function, right? But if I look at the ends of my function, as I go to the right, the e function goes to infinity. As I go to the left, I'm approaching 0. I'm not ever going to cross. It's going to approach 0. So the limit on number 15 as x goes to negative infinity. As I go more and more and more and more and more negative to infinity, I'm getting closer and closer and closer to 0. As I go to infinity, as I move further and further and further to the right, I approach infinity. Or it does not exist. Well, I like infinity a lot better in this situation because I don't have that same asymptote. So I'm okay with the infinity on that one. Now, number 17, the limit as x approaches infinity of e to the negative x plus 2x squared minus x divided by x squared plus 3. Everyone's going to panic. Oh my gosh, there's so much going on. So first of all, let's clean this up. As x goes to infinity, e to the negative x, that's just 1 over e to the x, okay? Plus 2x squared minus x, I don't care about the minus x because I'm going to infinity. So all I really care about is the 2x squared. And on the bottom, I don't care about the plus 3. All I care about is the x squared. So as I am thinking about what's happening as I'm going to infinity, 1 over e to the x, we just decided as I'm going to infinity, e to the x is going to a really, really, really big number. So 1 over a really, really big number equals 0. All right, 2x squared over x squared. As those go into infinity, they're the same, they have the same exponent of 2. So all I care about is the numbers out in front, which is a 2. So 0 plus 2, my limit of that messy thing as x goes to infinity is just 2. Okay, 18. As x goes to infinity, 2x squared plus 4x, again, I don't even care about the 4x. E to the x plus 3x squared, which one of those is bigger? Which one of those is going to grow faster? Well, e to the x is going to grow a lot faster because x is getting bigger and bigger and bigger and going to infinity. So as this goes to infinity, again, I've got, my bottom is a lot bigger than my top, significantly bigger than my top. And we said that when that happens, when it's bottom heavy, my limit is, do you guys remember? 1 over a really big number, my limit would be 0. Okay, as for the homework, 1.3 homework, all the numbers in 1.3, I want you to do all the problems, but I don't want you to do 33. 33 uses that function that we are avoiding because we don't use it in this class.